Hello, everyone. Welcome back. Today, we are going to talk about gradient descent, how it is used in machine learning, what are the different types of gradient descents, algorithms, and also see a practical example of it. But first, let's clarify what is gradient descent. It is used extensively in machine learning. So, it's important to have the concept clear. We're going to take an example, see step by step how gradient descent helps in reducing our loss of our algorithm. Okay, let's go ahead and get started. So, where did the term gradient descent comes from? It comes from two words, right? It's gradient and descent. Descent automatically it means going down, like reducing. Now, gradient is nothing but a vector, it is a point. It points the direction. So it's a set of points where which increases if you take that step towards that direction, your loss will start getting lower and lower, which means in turn, your model will start performing better and better. Or again, put in another words, your model can start predicting values closer and closer to the actual values, which means it starts performing much better. Okay. Now let's go ahead, see the next one. So why gradient descent? Okay. So the model updates its weight by moving in the direction that reduces the loss function the most. So what does the loss function do? It computes the total loss. Now, when I say loss, it simply means how much did the predicted value of the model differ from the actual value. Okay, so it's a sum loss function. What it does, it summarizes everything, which means it adds up everything, and the total figure that you get, that is your loss function. Now, we want the loss to be minimal, as low as we can, which means we want the model to predict the values as close to the real values. Think of it as like hiking down the mountain. So, gradient descent, what it does, it finds the path where the mountain is steepest, which means in less number of steps, you can reach your minimum. Now let's go with an example. Enough of talking. So let's assume X is our feature, 1, and it has the value 1, 2, and 3. Y is our actual values. So when X is 1, Y is 2. When X is 2, Y is 2.5. When X is 3, Y is 3.5. Now we want to develop a model which will read the values of X and learn itself how to get the values of Y, or get as close to the predicting to the values of Y's. So what we do is we assume random weights, okay, 0.5, 0.5. So one is the bias, one is the actual weight of the feature, and learning rate, like how much it should differ. Right now, we start with 0.1. Again, we just assume. All these are random values that we assume in the beginning. So again, this is our initial data set. Okay. Now, step 1, compute the prediction and the loss. So for the prediction, the model uses this formula, y hat, which means the predicted value is equal to the bias plus the weight times x. Xi means whichever position the x is. Like we had 3 values, right? So xi, x0 will be 1, x1 will be 2, x2 will be 3. So here, and for the initial weights, W0, which is the bias, and weight 1, which is 0.5, assumed simply the same. There's no particular reason between selecting these two the same. The predicted value, so because we are using this formula, is 0.5, that is bias, plus the weight times the actual value. And it predicts this for y. The actual value of x is 2. And here in this case, the value of x is 3. So using this formula, a model predicted that the value of y will be 1, 1.5, and 2. What should be the actual values? 2, 2.5, and 3.5. So what is our loss? 2 minus 1, or rather 1 minus 2, or y hat minus y, which is this 1 minus 1. Y hat here is 1.5 minus 2.5, which is again 1. 2 minus 3.5 is minus 1.5. So this is our loss. So loss function, which will be, the total loss function would be adding up of all these three. So it would be minus 3.5. Now we compute the gradients. Okay. So which means, what do? We predict the new values of the bias and weight, using which our loss function will reduce. Okay. So we randomly started with 0.5 and 0.5. We picked some random values of bias and weight. We applied our formula and the model predicted some values. Now we know that the values are nowhere close. So now what we do is, this is our loss as compared to weight 0. This is our loss as compared to W1, which is the weight and the bias. And this is our formula, summit y hat minus yi 2 upon m, where m is the total number of elements, which in our case is 3. We have 3 samples in our data set. Applying these two values, so the gradient of W0, or the bias, is 2 by 3 times, see the sum of all our losses, minus 1, and minus 1.5, which was minus 3.5. You multiply this and you get minus 2.33. So the new weight is minus 2.33, and the new value for W1, the new bias is 2.33, and the new value for weight, W1, applying the same formula, is minus 5. So for weight, we use this y hat minus y1 times the value of x. Okay. So all these three, minus 1 times 1, minus 1 times 2, and minus 1.5 times 3. Again, this minus 1, this minus 1, and this minus 1.3 is our loss, which we computed in the previous step. So which gives, expanding this formula, gives us the value minus 5. So now we have new values for weight and for bias and weight, or W0 and W1. Now we will use these values in, again, the formula. Okay. So we have to apply the learning rate too. Okay. So which means the initial value, the learning rate that we assumed, which was 0.1, the new value that we computed for W0, which was minus 2.33, gives us the new value for W0, which is 0.733. Same thing we do for W1, the initial weight minus the learning rate minus the minus 5 value that we computed in the previous step, which gives us the value 1. In the next iteration, so this is one iteration. In the next iteration, instead of using 0.5, 0.5, the default values that we assumed, now we are going to use these new values, which we found out using the gradient descent formula. So now x remains the same, actual values remain the same. Now, y hat predicted using the same formula W0 plus W1 times xi gives this. So W1 was 1 and W0 is 0.33. So now this is our new predicted values, or these are our new predicted values. Now our loss, as you can see, is reduced considerably, right? It was minus 3.5 initially, and now it's reduced. Again, the model is not perfect yet. So what we do, use the same formula. We compute the gradients using the same formula that we used earlier for W0 and W1. We got this for new values. We update the weights using the same procedure. And now we get new values or for W0 and W1. So this is our new bias. This is our new weight. So step 1, it was 0.5, 0.5, which means we picked some random values or random point. We computed our loss. Now we got this. We got the new values. Here we have it. And then we computed our new loss using the new values of W0, W1. We repeat the same set, okay? Now let's see what values we get with these new values of W0 and W1, or rather, what is our new loss when W0 is 0.72 and W1 is 0.94. Here it is. Using this, again, as you see, the loss keeps getting lesser and lesser. So what does it mean? The new predicted value gets close to the actual values. See, 1.66, 2.6, 3.54. Okay, with the third iteration. So this is the updated weights again. So we keep on doing it until our predicted values are as close to the real values. Okay, this example just shows 3 iterations, but you don't have to stop at 3 iterations. Okay, so after 3 iterations, the value of W0 is roughly this, so which means our bias is this, and our actual weightage for our feature X is this. Okay, so we are seeing that the weights are converging towards better values. Okay, so this is what gradient descent is. Now, this is done with multiple features. This example just made to simplify the explanation, we are using just one feature. We can have multiple features, okay? And that is what this real life scenario is. You don't have just one feature, you have billions of parameters for training, okay? Now, this is actually what gradient descent is, which means you are trying to get the rough values or approximately the values of weights and biases using which your model can predict values which are close to the or close to the actual values, not exactly identical or not exactly the same, which means you're overfitting, but you have to be as close to the values as possible. There are different types of formulas available to compute the gradient descent. We have batch gradient descent, okay, which is this formula. We have stochastic gradient descent, which is a different formula. So this is theta, model parameter at step t, learning rate, gradient of the loss function with respect to theta, computed over the entire data set. Now, stochastic gradient descent just uses one data point, okay? See, each data point rather than the whole data set. So that's the main difference between the two. Mini batch, it's a combination of two. So you don't take the entire data set and neither do you take just one point, okay? You go somewhere in between, like you take a sum of mini batch. Okay, M. So if let's say you have 100 parameters, M would be say about 20, 30, or however whatever batch you want. Okay. Then there is momentum-based gradient descent. There is Nesterov accelerated gradient, different formulas, different types, each having its own different formula. So the only thing difference is the formula being used to compute the new values. The goal remains the same, to have the model perform much better or predict values which are closer to the actual values. Okay. But just the difference is the formulas that you're using. Now, where do you use batch gradient distance? In small data sets. Stochastic, we are using in large scale machine learning. Mini batch gradient descent in mostly in deep learning models. Momentum based training deep neural networks. And Nesterov accelerated gradient is used in optimizing deep networks, reinforcement learning. Okay. Now, let us see an example in Python. How does like a visualization of gradient descent? Okay. So this is our gradient descent.py. We will use NumPy and matplotlib to plot. So we just simple loss function we define. It's w squared. The gradient is 2 times the weight. Learning rate is 0.2. In the example that I showed on the slide, we had 3 iterations. Here we are going to use 10 iterations and see how the model is, the loss gets reducing and reducing. We just apply the formula, and this is just to plot it. Okay, let's run. Python gradient descent. See, this is with 0.2 learning rate. Okay, this is how our plot looks. See the gap between these two, the first and that's a huge jump. Okay, now let's reduce our learning rate. Let's make it 0.1 and see what happens. Go back here. Now see the gap reduced in each, right? 1, 2, 3, 4, 5, 6, 7, 8, and 9, 10. So by the time it's 10, your loss is so low, right? Now let's increase it drastically. Let's make it 0.5. What happens? If we go to 0.5, see, in just 2 steps, the model learns. But again, it's not ideal to have a model, what you can say, learn it in just 2 steps, because while training, it will be okay, but while testing, it might not do better. Okay. And what I've heard is all these new models that are coming out, in order to show their accuracy in prediction and make their figures look good, what they do is they overfit their models so that when compared to the other model that's coming out in market, you say, oh, our model predicted the values with much better accuracy. So the prediction is much better using our model and all. But again, they are trying to overfit. They're trying to sell you their models. But anyways, that's a different conversation. But again, see the gradient descent steps. So in 2 steps, the model learned. Okay, that was with 0.5 learning rate. With 0.3, again, if we see, the model took certain steps and it is as close to 0 as possible. So our loss function is, the total loss is almost 0, which means the model predicted exactly the values that we wanted it to do. Okay. So that is it about gradient descent. So once again, what it is, we start with some randomly picked values. We use a formula that works best in our scenario, and we keep on computing new values for our weights and biases so that our model can perform better and predict values more accurately. Okay. Learning rate, we saw how it affects learning, it affects the performance of our model. We don't want it to be too high. We do not want it to be too low. If it is too low, the model will learn very slowly. If it is too high, you will run into overfitting. Okay, you might overshoot. All right, this was all about gradient descent. Hopefully you liked it. Feel free to ask any questions. Like, subscribe, your choice. All right, thank you all for your time and see you all again in next session. Thanks all. Bye.